Good morning, or maybe good afternoon, or maybe good evening. I hope that you're having a good day so far. It's about to get better as we study power series solutions of differential equations. In section 3.1, we're really just going to scratch the surface of this method, and the purpose is to introduce you to this method. It's not necessarily going to be a comprehensive coverage, but I want to give you an alternative to solving higher order differential equations with non-constant coefficients. This is really a fascinating method, in my opinion. Part 1, we're going to talk about linear differential equations with variable coefficients. Differential equations with constant coefficients can be reduced to the algebraic problem of solving the characteristic equation. So that's a very simple and straightforward method where we reduce the calculus down to an algebraic problem. However, when we have variable coefficients, this generally requires the power series method. For example, we've got two famous differential equations here. One is called Bessel's equation, the other one's called Legendre's equation. Notice that both of these are linear differential equations. Both of these are examples of second order differential equations, but also observe that they have non-constant coefficients. So these examples are a little different than the differential equations we learned in both chapters 1 and chapter 2. Now, in chapter 1, which was probably a little more difficult than chapter 2, we were studying differential equations with non-constant coefficients, but they were only degree 1 equations. We looked at methods such as direct integration, separation of variables, applying an integrating factor, and making a substitution to solve those differential equations with non-constant coefficients. Then in chapter 2, we were looking at higher order differential equations, but these only had constant coefficients. That's always good news when you have a linear differential equation with constant coefficients, because you can solve it very quickly and efficiently. So these two equations are different in the fact that they are higher order differential equations, that is, these are degree 2 equations, and they have non-constant coefficients. So the methods that we've learned will not apply to these two equations. We will study a new method for solving these types of differential equations using power series. Now, you learned about power series in Calculus 2, but this is a very detailed area of calculus, so we're going to review some important definitions before we begin applying this to differential equations. You probably remember from Calculus 2 learning about determining if a series converges or diverges. You spend plenty of time looking at series composed of the sum of an infinite number of constants. Then you're going to throw a variable in the mix. When you get a variable in your series, it's called a power series. So note that the difference between a power series and just an ordinary series is that a power series has a variable x. Let's look at an example of a basic power series. We have the sum from n equals 0 to infinity of c sub n times x minus a to the nth power. So here the lower limit of summation is 0, the upper limit of summation is infinity, so this is an infinite series, and our variable here is x. Both c sub n, a, and n are going to be constants. The index of summation here is n, and I can see that index associated with this coefficient and this exponent. So with each term, that index increments by 1 each time. If we expand this power series, it's going to look like c sub 0, notice this is the 0th term, and again, if I plug 0 in for n here, that term becomes 1. So the first term in our power series is c naught. For the next term, we're going to increment our index by 1. We're considering n equals 1. So we end up with c sub 1 times x minus a to the first power. For the next term, we will increment our index by 1, getting n equals 2. So we end up with c sub 2 times x minus a squared. And then we continue this process. The dot, 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 or the ellipsis indicates continue this pattern. Here is the nth term. This is a general representative of each term of the series, known as the nth term. That's a very powerful formula that will be useful to us. And notice we have a plus dot, 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 another ellipsis here showing that this pattern continues indefinitely. So if I zoom out and look at the big picture of the structure that I have here, we happen to have a polynomial function of infinite degree. Notice the exponent is in ascending order simply because we can't start with the infinite power and descend. So we start with the constant term and we ascend up to a power of infinity. Now a is called the center of the power series. If you think about it as a transformation on the graph, when we subtract a constant from x underneath that power, it just shifts the graph to the left or to the right depending on the sign of a. If we center this at 0 for a equals 0, then we get a very simple power series. We have the sum from n equals 0 to infinity of c sub n times x to the nth power. Expanding this, we would obtain c naught times x to the 0th power, which is 1, plus c sub 1 x to the first power plus c sub 2 x squared, and we can say this pattern continues. Let's go ahead and figure out the general representative of our terms. It's going to look just like our formula that we have right here. That's our nth term formula, or the formula for the general term. And because our upper limit of summation here is infinity, we'll do plus dot, dot, dot to show that this continues indefinitely. Now, looking at this clean example, we can very clearly see this is a polynomial function of infinite degree. So this is what we're calling a power series. Once again, in Calculus 2, you spent a considerable amount of time determining if constant series converge or diverge. Recall all of the tests you learned. You studied geometric series, you studied telescoping series, you looked at all kinds of tests such as the nth term test or the divergence test, the ratio test, the root test, on and on and on. Those things apply to constant series. They also apply to power series. Again, the difference between just a general series and a power series is that a power series contains a variable x. Now, recall that the power series from n equals 0 to infinity of c sub n x to the nth, the one we just expanded, converges on some open interval I, provided the sum from n equals 0 to infinity of c sub n times x to the nth power, our series, which is equal to the limit as capital N approaches infinity of the sum from n equals 0 to capital N of c sub n x to the n. So what I see right here is very similar to what I have here. The difference is the upper limit of summation. The upper limit of summation in this second summation notation is finite. Capital N represents some finite integer. So what I have right here is a partial sum. I'm just going to sum the series out to some finite index capital N. Then if I let that capital N tend to infinity, that generates the infinite series. So this little equation here is simply to remind you that the sum of a series is equal to the limit of its partial sum. If that limit exists for all x in this open interval I, then we say that the series converges. From your previous calculus classes, you learned about some special power series, and I want to remind you of two of those special power series. They're called the Taylor and Maclaurin series. These can be used to derive power series representations of elementary functions. This is going to be really important to our process of solving differential equations using power series. So let's review these two very important series. The first one is the Taylor series, named for the mathematician that pioneered this definition. It's the sum from n equals 0 to infinity of, notice in parentheses here, we have an exponent in parentheses that indicates a derivative, not an exponent. So we're looking at the nth derivative of a or the nth derivative of f evaluated at a divided by n factorial times x minus a to the nth power. So f of x represents some elementary function. Taylor showed that you could take an elementary function, such as e to the x, cosine of x, 1 over x, and represent it as an equivalent power series. What that means is that our elementary functions are all equivalent to polynomials of infinite degree. I think that's so fascinating. You can take any function and find an equivalent polynomial function of infinite degree. Now, let's practice expanding our Taylor series. So we're going to start at n equals 0. If we plug 0 in for n in all of these places, the first thing we see is the 0th derivative of f evaluated at a. What in the world does that mean? Well, if I'm talking about the 0th derivative, that means I'm not taking a derivative. We interpret that to be f of a. Also in the denominator there, we have 0 factorial. 0 factorial is defined to be 1. Okay, so we have f of a divided by 1 times x minus a to the 0th power. Well, x minus a to the 0th power is just 1. So our first term here is f of a. Next, we're going to look at the term with n equal to 1. This is going to be the first derivative of f evaluated at a divided by 1 factorial, which is just 1, times x minus a to the first power. Looking at n equals 2, we would obtain f double prime of a, f double prime of a divided by 2 factorial, which is just 2, times x minus a squared. We would continue. I'm going to go one more term just to be clear. F triple prime of a divided by 3 factorial. 3 factorial is 3 times 2 times 1, or 6. I'm just going to leave it in factorial notation here, times x minus a to the 3rd power, continuing. Okay, now remember, the f in the Taylor series represents some sort of elementary function. That may be e to the x, it may be 1 over x, it may be sine of x. Again, we'll look at some examples of that. So if I can take that elementary function and find its derivatives evaluated at the center point A, then I can rewrite the elementary function as an infinite power series. That is, an elementary function is equivalent to a polynomial of infinite degree. And by the way, that's how your calculator thinks about functions. I know you have buttons that say e to the x and sine of x, but your calculator actually evaluates those functions using a polynomial expansions. Now, Maclaurin is a special case of the Taylor series. The Maclaurin series is simply the Taylor series centered at 0. So if I let a be equal to 0, then we obtain the Maclaurin series. Let's go ahead and practice expanding the Maclaurin series. So for n equal to 0, remember we have the 0th derivative of f evaluated at 0 divided by 0 factorial. That simply gives us f of 0 times x to the 0th power. If we let n equal 1, we obtain the first derivative of f evaluated at 0 divided by 1 factorial. I just want to write that f prime of 0 times x to the 1st power. Next, we let n equal 2, so we have f double prime of 0 divided by 2 factorial times x squared. Let's go one more term. F triple prime of 0 divided by 3 factorial times x cubed. And this continues indefinitely until we have a polynomial of infinite degree. So those two methods can be used to find a power series representation of any elementary function. So let's look at the results of the Taylor and Maclaurin series applied to some common elementary functions. And this is going to be really important to our study of solving differential equations using a power series method. So part B, elementary functions as power series. Using the Taylor and Maclaurin series, we can represent many elementary functions as power series. So if we let cosine of x be the f of x in our definition here, and we're going to center this at 0, and we expand it we end up with a power series that looks something like this. 1 minus x squared over 2 plus x to the 4th over 4 factorial minus, notice that's an alternating series. Every other term changes sign. Now, if I take that series and I figure out what does the nth term look like, that is, what's the formula for each of those terms, I can then condense it into summation notation. So this is a concise way of expressing that polynomial of infinite degree. So we have the sum from n equals 0 to infinity. Negative 1 to the nth power is what achieves the alternating sign from term to term. We have only even powers of x, x to the 2n, and we're dividing by an even factorial. Again, where does that come from? It comes from applying this expansion to cosine of x. You're going to find with both sine and cosine, some of your coefficients, as generated by this term right here, turn out to be 0. Cosine of 0, sine of 0, that's what creates a series only of even powers or only of odd powers. Some of those are going to have coefficients of zeros, and that's why we lose those terms. So here you can see the power series expansion of cosine or sine. You can see the power series expansion of e to the x. That one's a pretty straightforward power series. And once again, if you use your graphing calculator to evaluate e squared or sine of 30 degrees or something like that, your calculator doesn't have all of the possible values of sine and cosine programmed in and taking up memory space. Instead, your calculator is using a power series of a specific degree. It doesn't go up to an infinite degree, of course, but it evaluates it according to a certain error threshold. So it's going to use a high enough degree or a high enough number of terms to evaluate your elementary function within a certain error threshold. So behind what the buttons that you see, you've actually got power series there. Now, let's look at the power series expansion for hyperbolic cosine and hyperbolic sine, just for practice. Over here on the right, we've got hyperbolic cosine. Here is the summation notation for the power series expansion, and we're just going to look at what the terms are. So starting with n equals 0, we have x to the 0th power, which is 1, divided by 0 factorial, also 1. So our first term here is 1. Letting n equal 1, we end up with x squared over 2 factorial, which reduces to 2. Then letting n equal 1, okay, sorry, here's n equals 0, n equals 1. I'm going to write it down so don't mess it up. N equals 2. We have x to the 2 times 2, that's x to the 4th power, divided by 4 factorial, okay? And you can begin to see we're going to end up with even powers and even factorials in the denominator, plus ... Okay, so we know that hyperbolic cosine can be expressed with exponential terms, that is e to the x plus e to the negative x divided by 2, but now we also see it's also equivalent to a polynomial of infinite degree. Hyperbolic sine is similar. The difference is that we're going to get the odd powers of x. So expanding our summation notation, if n is equal to 0, we end up with x to the 1st power over 1 factorial. If n is equal to 1, this is 0, this is 1. If n is equal to 1, we end up with x to the 2 plus 1, or 3 divided by 3 factorial. For n equal to 2, we'd end up with x to the 5th over 5 factorial. Then you can kind of see the pattern forming. Odd powers of x divided by the corresponding odd factorial, okay? Now, because we know the exponential definitions of hyperbolic sine and hyperbolic cosine, if we add those two terms together, hyperbolic cosine plus hyperbolic sine, notice we would simply end up with e to the x. So if I take the two power series expansions that we just considered for hyperbolic cosine and hyperbolic sine, and I add them together, then I'll have every power of x. And notice that's what e to the x is over here. So you can see the relationship between those terms. Let's do one more practice expansion. Let's look at the natural log of 1 plus x. This one, observe, is a little different than the others. I put it in bold print to catch your attention here. This is the sum from n equals 1 to infinity as opposed to 0 to infinity. So letting n equal 1 in this example, starting with n equals 1, we'd have negative 1 squared, which is positive 1, x to the first power over 1. The second term, n equals 2, notice we're going to have negative 1 to an odd power. That's going to generate a negative term. And if n is equal to 2, we end up with x squared over 2. For n equal to 3, we're going to have negative 1 to an even power. That makes a positive 1, x cubed divided by 3. Okay, and this is an alternating series. That means the sign switches term from one term to the next. Now, this is going to be important to our power series solutions of differential equations, because ultimately we're going to end up with solutions that look like these polynomial expansions. Once we figure out those polynomial expansions, and often we're going to convert them into summation notation, then we'll be able to recognize that power series expansion represents some elementary function. So keep this table handy here under option B as you solve your homework problems. That's how you're going to convert your solutions back to an elementary function. So continuing to part 3, we want to study now the power series method for solving differential equations. Before we jump into a method, there's just a little bit more preliminary review information that I want to give you. So this is going to work in a similar way that we did linear equations with constant coefficients. We assumed a particular solution. Remember, we said assume that the solution is y equals e to the rx, and that was what we used to generate a characteristic equation. So for a given differential equation with non-constant coefficients, we're going to assume a solution in the form of a power series, okay? So we're going to assume that y, the solution to the differential equation, is equal to the sum from n equals 0 to infinity of c sub n times x to the nth power. Now remember, that can represent any elementary function. If we can determine the coefficients, then we could equate it to one of our elementary functions, and we're simply going to have a power series representation of the solution. So we're assuming that the solution to the differential equation can be represented by a power series. We're going to take this assumed solution and substitute it into the differential equation, just like we did with y equals e to the rx for higher degree linear differential equations with constant coefficients. So we're going to plug it in, and then we're going to determine the coefficients. We're going to have unknown coefficients. However, this time we're going to have an infinite number of unknown coefficients to determine. So recall that we studied the method of undetermined coefficients along with variation of parameters. Now we're just going to have an infinite number of unknown coefficients, but the process will essentially be the same. The solution is then going to be the power series representation of the solution to the differential equation, which we can convert back into its elementary function form. So that's kind of the overview. Assume a power series, plug it in, find the coefficients, and then attempt to discern which elementary function your power series solution represents. So just a bit more preliminary information. I'm not going to spend too much time on this, but for a power series of the form sum from n equals 0 to infinity of c sub n times x to the nth power, let rho equal the limit as n goes to infinity of the ratio, absolute value of the ratio c sub n over c sub n plus 1. If this limit rho is equal to 0, then the series diverges for all non-zero x values. So notice here I'm taking one term and dividing it by the next term. If the limit is equal to 0, that means the denominator is larger than the numerator as n approaches infinity. This is going to cause the series to diverge. If rho is positive and finite, another way of saying that is rho is between 0 and infinity, it's positive and finite, The series will converge if the absolute value of x is less than rho and absolute value of x greater than rho indicates divergence. This should remind you a lot of the geometric series. If you think about the conditions for when does a geometric series converge, it looks a lot like rho. And rho here is very similar to the R from the geometric series. By the way, I'm going to put some links in the description box that will connect you to videos over series and power series and Taylor and Maclaurin series in case you need a review. Okay, they're optional, but they'll be there if you need them. Finally, if rho equals infinity, the series converges for all x. Rho is what we're calling the radius of convergence. So for what x values does the power series converge to that elementary function? Okay, so we'll briefly acknowledge the radius of convergence as we go through these examples, but our primary goal here really is to learn how to solve a differential equation using this new power series method. I also want to remind you that we are just scratching the surface of this method. And the purpose of this video is to show you how this method works. You're going to see it gets pretty complicated pretty quickly. And so in general, if you need to solve a differential equation with the power series method, you're often making use of a computer algebra system, such as MATLAB, for example, that can handle all of these calculations that we're going to do. So what you're going to see in our examples is that we're going to be solving very simple differential equations. We're going to start really easy so that we can see how this power series method works. But on example 1, y prime equals 4y, notice I could solve that in about 30 seconds with the separation of variables method. Okay, so you're going to see the power series method is a lot more complicated than solving this by separation of variables. So my purpose is to start with an easy one so that we can learn this power series method. But if I had the choice, I'm solving that one with separation of variables. All right, so solve, we want to find a power series solution to first order constant coefficient differential equation y prime equals 4y, and then we're going to identify the corresponding elementary function. So we're going to make an assumption about the solution. The solution to this differential equation is y. So we're going to let y equal, notice I'm assuming the solution here, okay? We're going to assume that it's in the form of a power series. N equals 0 to infinity of c sub n times x to the nth power. So if I can figure out the coefficients of this power series, then I'll be able to discern which elementary function it is connected to, and then we will have solved our differential equation. Now, we need to plug this into our differential equation. Our differential equation also has a y prime, so I need to find y prime. Now, if I look at the nth term, it's just a constant coefficient times the power of x. So to differentiate that, we're going to take our constant coefficient c sub n, and we're going to bring our exponent n down in front as a coefficient and decrease n by 1. So before I figure out my limits of summation here, I'm going to notice here's the pattern of the derivative, right? Take the power down in front, keep your constant, and decrease the exponent by 1. But for example, if I look at a simple polynomial, okay, and find its derivative, I notice that the derivative has one less term than the original function. So instead of counting from 0 to infinity, which by the way, if we plug in 0, my first term is annihilated anyway, we're going to start counting from n equals 1 to infinity, okay? So somehow indicate in your notes, I'm going to highlight it here in red, that index changed. That's a little detail that's easy to overlook sometimes. Okay, we're going to take this assumed solution and we're going to sub it into our differential equation. Our differential equation is y prime equals 4y. So y prime in power series form is the sum from n equals 1 to infinity of n c sub n x to the n minus first power. On the right side here, we have 4 times y, and y in power series form is the sum from n equals 0 to infinity of c sub n times x to the nth power. Notice my goal here is to find the coefficients c sub n. So on both sides of this equation, I have a power of x. We can assume that the coefficients of corresponding powers of x are equal. However, I have a little bit of a problem. On the left side, I have lower limit of summation n equal to 1, and on the right side, n equal to 0. I prefer that those are the same so that it'll be easier to set our coefficients equal. So I'm going to make a change. I'm going to change this lower limit of summation to 0. So I'm subtracting 1 from the lower limit of summation to make it 0. If I subtract 1 from the upper limit of summation, infinity minus 1, we still get infinity. Okay. Now I can't make that change just because it's convenient. I have to make sure that this step appropriately represents the previous step in an equivalent way. So if I decrease my index of summation by 1, I'm going to cancel that out by increasing the index of summation n by 1 in our nth term formula. So we're going to write this as n plus 1 times c sub n plus 1. Adding 1 to n here is going to give us x to the nth power. Okay? And over here, just as a reminder, you can factor constant coefficients inside and outside of that summation sign. Okay? Now, both sides have the same index of summation. They both count with 0. They both have corresponding powers of x, x to the nth power. So now we can jump to the conclusion that the coefficients of corresponding powers of x are equal. Okay? So I'm going to take coefficient only, n plus 1 times c sub n plus 1 equal to coefficient 4 times c sub n. So really, we have an infinite number of unknown coefficients here. And I'm setting them corresponding coefficients equal simultaneously by using that subscript. Okay, now my goal is to figure out what's the pattern of these coefficients. So I'm going to solve for c sub n plus 1. Okay, c sub n plus 1 is equal to 4c sub n divided by n plus 1. This is what we call a recursive formula or a recurrence relation. The preference is an nth term formula. Okay, by recursive or recurrence relation, we have each coefficient in terms of the coefficient that came before, right? C sub 1 depends on C naught. C sub 2 depends on C1. My goal is to find an nth term formula. That is, I want to express the general term in terms of its position in, not in terms of the previous constant C sub n. Okay, again, if you need to review that information, I'll attach some in the description box, some videos where you can go back and review all of that detailed technical information. So our goal here is to figure out the constant coefficient c sub n as a function of its position in. This is called the nth term formula. Okay, and to do that, I'm just going to generate a pattern and see if we can inductively determine what that nth term formula is. So suppose that n equals 0. Okay, if n equals 0, using our recurrence relation here, we'd have c sub 0 plus 1, or c sub 1, is equal to 4c naught divided by n plus 1. 0 plus 1 is 1, so here c sub 1 is equal to 4c naught. Okay, let's increment our index by 1 and see what happens. So again, I'm using this to generate these little equations. If n equals 1, we have c sub 2 equals 4 c sub 1 over 1 plus 1, or 2. Okay, now the temptation here is to cancel the 2 into 4 and make it 2c sub 1, but I'm not going to do that because I want to see how the pattern develops. So I'm going to leave the coefficient as 4 over 2 and resist my desire to simplify and replace c sub 1 with what we found up here. That's 4c naught. Okay, let's do this again. Let's suppose n equals 2, and let's use our recurrence formula here. to figure out the next coefficient. C sub n plus 1 this time would be C sub 3 equals 4 C sub 2 over 2 plus 1, which equals 3, okay? So this is going to be 4/3 times C sub 2, and remember we found C sub 2 previously, 4 over 2 times 4 C naught. So I'm looking for a pattern that can form that I could inductively say, okay, once I know this pattern, now I can jump to the general nth term, okay? So let's make some observations about the pattern we've developed so far. When n equals 1, we have 4 to the first power times C naught. When n equals 2, we have 4 squared times C naught, and we have a 2 in the denominator. When n equals 3, notice we have 4 to the third power times C naught, and I'm seeing a factorial develop here in the denominator. So we can jump to the conclusion inductively that C sub n is going to be 4 to the nth power times C naught divided by n factorial. So this is what we call the nth term or general term formula. That is, the coefficient C sub n is now in terms of its position in the series, n, as opposed to being dependent on the previous constant. All of our constants are dependent on C naught, but each constant is not dependent on the previous term. This is a big deal. Now we can go back and say, therefore, the solution to our differential equation, the 3 little dots mean therefore. Remember we had a pattern over there. It was the sum from n equals 0 to infinity of C sub n times x to the nth power. Well, now we know more specifically what those constants should look like. We have the sum from n equals 0 to infinity. We'll replace C sub n with what we found, 4 to the nth power times C naught divided by n factorial times x to the nth power. So if we simplify this, C naught is common to all infinite terms of that series, so we can factor it out as a greatest common factor. Also notice that both 4 and x are raised to the nth power, so we can group those together, 4x to the nth power divided by n factorial. So we have solved the differential equation. It's just in terms of a power series. Now I need to figure out what elementary function corresponds to this power series. So we have 4x to the nth power divided by n factorial. If we come back up here to our table and we look at all of our elementary functions, we want to figure out which one is most closely resembles the function that we just generated. We had 4x to the nth power over n factorial. So if you'll notice right here, we have a power of x over that same factorial, power of x over, that's really close to what we have, but the difference is in our solution, we had 4x raised to a power over n factorial. Well, if I simply replace this x right here with 4x to the nth power, that's going to change each of these values to be 4x raised to that power, and that simply means I'm evaluating this function at 4x. Okay, so replacing all of the x's in this formula with 4 x's, including the one over here to the left, the elementary function, we discover the solution then is e to the 4x. We can come back to our power series solution here and say, therefore, y is equal to c naught, and replacing our summation notation here with its elementary function, c naught e to the 4x. And of course, we could determine that c naught using an initial condition. By the way, when we have elementary functions, our radius of convergence here is infinity. So that is a power series solution to a very simple differential equation. Now, just for fun, just for entertainment purposes, I want to go back to this differential equation for a minute. It's dy over dx equals 4y. I mentioned at the beginning we could solve this with separation of variables. So I'm going to do that very quickly. Okay, I've separated variables. I'm going to integrate both sides. We get natural log of the absolute value of y equals 4x plus c. Solving for y, we would get y equals e to the 4x plus c. And as we've seen many times, this is c e to the 4x. Okay, so that is equivalent to what we have over here. One is called c naught, the other one is called c. That took like 30 seconds. So again, the purpose of this lesson is to show you how the power series solution works. As you can see, it gets pretty complex pretty quickly. And so it's necessary that we start with a very basic differential equation. So if I were to solve this differential equation by choice, of course I'm going to go with separation of variables, but now I know a little something about the power series solution. So on the next example, we will look at solving a differential equation with non-constant coefficients, and we'll see how the power series method applies in example 2.